Welcome again, my friends and followers. Let us talk about condensation, heat transfer coefficient. How can we estimate the condensation heat transfer coefficient of fluids as they pass through the tubes? It is meant here to talk and present the condensation process when we have internal flow in the tubes. Let us go to some details of this subject. Welcome, my friends and colleagues and followers. The condensation process is one of the important topics present in modern industrial applications in the field of energy and heat transfer. We may find the condensation process in many topics and fields of industry, such as petrochemical factories, refineries, food industry, power plants, air conditioning and refrigeration, and many other topics that is experienced in the field of thermal engineering. The prediction of condensation process and the performance of a heat exchanger is mainly based on the heat transfer coefficient and how accurate it has been predicted. Condensation can occur in different orientations: vertical, horizontal, single, or tube bundle. And in the present episode and the film episodes and videos, I will introduce the condensation process in different categories, whether it was external or internal flow. Thank you for your support and continuous assistance that is afforded by your side to the channel, and let us go directly to the objectives of the present episode. The objectives of the present episode are related to practical case study and how can we deal with condensation inside um, vertical tubes, and how can we predict the heat transfer coefficient of such a process, and then we will go to the closure. It is a quite short video just to introduce a case study for the condensation process in inside the tubes where a vertical tube is considered. The case study for condensation process, uh, we have a tube having path in BWG18 with 12.7 millimeter outside diameter and 10.21 millimeter inside the diameter with vertical orientation, where we have Freon 134A passes as a saturated vapor at a pressure 3 bar. Absolute passes through a vertical tube at the rate of 40 kilogram per hour, and we need to calculate or predict the condensation heat transfer coefficient. We have table 1, which represents the thermal properties of Freon 134A. We have the saturation temperature corresponds to 0.67 degrees Celsius, and the last row represents the critical pressure of this refrigerant, which corresponds to 40.59 bar. Solution, we will start with calculating of condensate tube loading, which corresponds to 0.347 kilogram per meter second, and we have the mass velocity and represented by capital G equal to 135.7 kilogram per meter square second, and Nusselt correlation as presented in equation 1a. If we substitute the values or the corresponding values of properties rho sub L, rho sub V, G the gravitational acceleration, and the mu represents the liquid dynamic velocity, then the heat transfer coefficient corresponds to 488.02 watt per meter square Kelvin, which represents the answer to this part. Then we will go to a correlation presented by Boito and Crusilin, shown in equation number 2. We first calculate the Prandtl number of the refrigerant 134A. It corresponds to 3.82, and then we have raw liquid, the Reynolds number for the mass as a liquid when we consider all the liquid passes or the vapor converted to liquid. Then we have G is the mass flow rate divided by the cross-section area, and if we substitute the values, then our Reynolds number sub L equal 5094. Then the mean heat transfer coefficient, as explained in the previous part of this subject, we have the mean heat transfer coefficient equal 319.7 watt per meter square Kelvin. Of course, to calculate the heat transfer coefficient of condensation, we have to include the effect of the density variation as shown in term between brackets 1 plus square root of rho sub L divided by rho sub V, and the total is divided by 2. Then the heat transfer coefficient corresponds to 1654.3 watt per meter square Kelvin. And the form of expression is valid for complete condensation, where we have saturated vapor has been converted to saturated liquid at the exit of this tube. let us summarize the results of the present case study. In this table, we have included the results from Nusselt, Boyko, and Crosilline, and we have added the results when we used Shah correlation as indicated in reference number 3. And the detailed calculations for Shah was not included in this episode, but you may go back to my published book entitled The Principles and Practice of Heat Transfer, and you may find more details about this correlation and other published models about condensation in vertical tubes. Of course, it's clear Shah correlation predicted almost 4 times that of Nusselt, and usually is referred to Nusselt equation as a conservative one, and that will lead to overestimate the surface area of the condenser, and it will be reflected on the cost and fabrication, maintenance of such heat exchangers. We should know that for condenser design, it is used to evaluate the condensing heat transfer coefficient for annular and stratified flow, and we usually should select the higher value in the calculation of the overall heat transfer coefficient of that heat exchanger. I have included more published work by others as well in my book, and you may go back to that and you may find the detailed address of this book in the description box below this video. Now we have arrived to the final section of the present episode, the closure. We presented a practical case study where the heat transfer coefficient for condensation of saturated vapor Perion 134A in a vertical tube, and how to estimate the heat transfer coefficient. We have some valuable resources in, in a PDF file with a link seated in the description box. Please visit that, and you may get some of them free from the internet and are available. For my publication, you may go to ResearchGate on my page, you may find them as well. And if you feel that the content of the present video are useful to you and others, please subscribe and share the information, and don't forget to hit the like button because that will increase the possibility of reaching these information to any person who needs them. Thank you for listening. I will see you in the near future. Bye bye.